Hi, this is Professor Fernandez. We're going to talk today about the equations of lines. This is the third module in lesson 3. In the first module, we talked about the cross product, and then in the second module, we used that to derive the equation of a plane. So in this module, we're going to talk about lines using some of the thoughts and approaches that we did to derive the equations of planes. I'm going to give you a very quick review of what we did there, just conceptually. Remember, in that module video, we had a plane, and we came to realize that its normal vector could characterize for us the orientation of the plane. And then we said, okay, great. So if I have this normal vector on the plane, and it's perpendicular, that's what normal means, to the plane, and I have a bunch of points here. Let's say the anchor points, which is on the plane p sub 0, the point p sub 0 on the plane. I want to use it to construct a vector from that point to some other point on the plane, let's say this one. And then we put everything in R3 and we started using those points to generate vectors from the origin. This was R sub 0, and this other point here, we called it R, so that this difference was R minus R sub 0. And then we saw back from the dot products properties that we had learned about in lesson 2 that the perpendicularity, the orthogonality of the normal vector with this new vector r minus r sub 0 meant that the dot product of those two was 0. And then from here flowed the equation of the plane that we talked about in the module 2 video. So to get to the equation of a line, we're going to do something very similar. I'm going to mimic this process, intuitively speaking, not exactly. First place to start is to recognize that just like a normal vector is essential to thinking about the equation of a plane, if I draw a line, and let's just start in R2, here is a line. We're certainly used to thinking of this as y equals mx plus b, but we can think about it now in terms of vectors a little differently. So let me actually move this line a little bit further up to make things easier. Let me also draw things bigger to make it easier to see. So here is my x, y axes, and let's draw this line here. So one thing that characterizes a line, kind of like the normal vector characterizes a plane, is the direction. So here is a line that I have drawn in this direction. That was the original direction that I drew the line in. So let's call this point, just like we did in the plane, p sub 0. And let's call this vector v, the vector that is pointing in the direction of the line. So v is going to play the role of n in terms of our thinking about lines, n being the normal vector for the plane. And then p sub 0 is going to play the same role as before. So what I'm going to do now is create vectors from the origin to these points, and then we'll understand how this gives us the equation of the line. So let's create a vector from the origin to p sub 0. Let's call that r sub 0. And then let's, for now, just create, kind of like we did before with planes, a vector to the terminal point of v. Let's call that r. We see from here that r equals r sub 0 plus v. Okay, great. So what if I, extended my line here, and let's see if I can do this to try to be sort of straight. I think I sort of succeeded. And then I drew another v vector right after the first v vector. What if I drew a vector from the origin to here? I'm not going to call that r, so now I run into a little bit of a discrepancy issue here between having two r's that mean different things. So why don't I call the first r r sub 1? For I have, there's only one v vector that I went along the line. Let's call this second vector r sub 2. So what have I done now? I've done r sub 0. I went from the origin to this point, and then I've gone 2 v vectors later, and then I get to this terminal point. So r sub 0 plus 2v. You might be able to see from here how we can easily generalize this. And if I went a third v vector, calling that r sub 3, I would get r sub 3 equals r0 plus 3v. So maybe if I went n vectors of v forward, I would have something like plus nv. And now let me go back to my picture and think about what would happen if I went backwards, right? So what if I went backwards by the v vector? Well, remember what we talked about, that if I think about my properties of vectors, a vector that's anti-parallel points in the exact opposite direction of a given vector is the same as multiplying that vector by a negative. So this vector is negative v. And then I could, through the same arguments that I did over here, write that vector from the origin to the terminal point. I'll call it r sub negative 1. I could write that as r sub 0 minus v. So, following the same exact logic, we could get to r sub negative n equals r sub 0 minus nv. So the picture we're building up is that this is the vector equation, this one, that tells us if I go n units along the vector v, up in the upper right direction, if you will, then this is where I end up. If I go n units along the vector v in the lower left direction, in other words, this way, this is the vector where I end up. And you can see that I've introduced things with n being a whole number. But now we're going to make the leap. We're going to say, oh, so what if I just replace n by any real number? What if I only want to go half of the length of v, or a third of the length of v, or backwards by 1/1000th the length of v? So I'm going to put a t here. And then the last thing I'll do is I'll say, this notation that I introduced makes sense. But now we're seeing this, kind of like a function, which is an interesting concept that we're going to explore further in a future lesson called a vector valued function. But I'm not going to say much more about that here, because we're going to talk more about that in a future lesson. But this is why I wanted to take this progression to ease you into this notation that is new notation, specifically this left-hand side. So this is what we've derived now. So we've derived this definition of the equation of a line. So let's go through it. So suppose I have an initial point and I make it into a vector. This is our p sub 0 up here in our diagram. So suppose I have that initial point, make it into a vector, and as I assumed up here, I have some initial orientation, which is the vector ABC. Then the equation that we derived over here is the equation of the line. So that's the initial point plus a multiple of v, where v is the direction of the line. So that's the equation of the line passing through P and in the direction of V. So this should make sense in this pictorial way, and I'm going to show you animations in a minute that will make it, hopefully make even more sense when you see this. Let's talk a little bit right before we do that about a different representation of this equation of a line. So what do I mean by that? Well, so first of all, let me also mention on the left-hand side, this L, obviously for line, is something that you'll see in a lot of textbooks, and I will also try to be consistent with that. Just to remind you that it is a line. It's a little different from the R of t that I used here. That's because this is the vector valued notation, which again, we'll talk more about that concept a little later. So for now, I am going to stick with the L of t just to remind you that these are equations of lines. Okay, great. So if we've gotten this far, this is good progress already, we can extract another representation of the equation of a line from this. How do we do that? Well, we were starting with the assumption that P was a point, that the terminal point of the vector P was the point x0, y0, z0, and that V was the vector ABC. So by my vector addition properties, I can write this as follows: plus TB, and then Z0 plus TC. There we go. And then from here, I can extract the parametric equations of the lines. So this is a function of t. I'm going to call it x of t. This is a function of t. I'll call it y sub t. And this is a function of t. I'll call it z sub t. So that leads naturally to this next definition. So suppose I am looking at the equation of a line passing through x0, y0, z0, and in the direction of v. Excuse me. The parametric form of this line is exactly what we just talked about. So, there are two ways to give the equation of the line. You could give it in vector form. That's what this is. You could also give it in parametric form. That's what this is. They both have their uses. In vector form, we got to this equation by thinking about how the vectors changed as I changed t. So that was really this picture up here. In parametric form, you're thinking about something subtly different. You're thinking about how the coordinates, the x, y, and z values of the vector change as t changes. So it ends up being the same thing, but a slightly different way of looking at it. Okay, so the last thing I want to mention before we start talking about examples down here is a comparison and contrast with what happens and what we know happens in 2 dimensions. So in 2 dimensions, lines are either parallel or they intersect. Right? We know this very well. So here's my xy axes, and here are 2 parallel lines. And then the moment I change I rotate one of these lines, even by the slightest amount, I am going to get a line that eventually intersects. So if I, change this line into rotating it just a little bit, if I continue this line, there's going to be an intersection point. So we know this. This is a fact in 2 dimensions. In 3 dimensions, there is an additional category to this. So lines are either parallel or they intersect or are skew. Okay? So what do I mean by skew? So skew refers to if I go in 3 dimensions and I think about the plane z equals 1, there it is. I think about the plane z equals 2, there it is. These planes never intersect. They are literally like if you took your sheet of paper I keep talking about, put it on your table, and then took another sheet of paper and put it right on top of that, but not touching it, parallel to it. Those would be 2 planes that don't intersect. And you can imagine then lines on each of these planes that go perhaps in opposite directions, if the picture makes sense. But, because of these planes never intersecting, these lines will never intersect either. So these are what are called skew lines. And I want to show you a picture because you actually have a lot of experience, most likely, with skew lines. So skew lines pop up in lots of places, particularly, so here I am on math.net, in freeways. So you can see here that this is an intersection, kind of 2 freeways. So you can think of this freeway down here as literally sitting on one plane, the roadway down here sitting on another plane, and then this appears to be a railway sitting on yet a 3rd plane. So, the lines that the cars are traveling along in these 3 different roads are all skew because they're on different planes, but, they're lines that don't intersect. So this is meant to be a very quick introduction to equations of lines and to this fact that in 3 dimensions, as usual, something is new and different from what we've seen in 2 dimensions. Great, so let's move now to solving some of these examples. First one we'll do is we'll talk about the equation of a line that passes through this point and parallel to this vector. So that's pretty nice setup for the first version of the equation of the line because we have a point and we have a vector that tells us the direction of the line. So I'm just going to apply this version of the equation of the line. So I'm going to write down my standard form here, and my point is I can convert into the vector p by just writing it as a vector. And then I have the vector v given. So, that's pretty much it. There's not much else to do from here. But one thing I will do, just again to link up what we just did, is I will combine this into these 2 vectors into one vector. And then I can extract from here the parametric equations of the line. Oops, not 1 plus 5t, but 5 plus t. And then y of t is 1 plus 4t, and z of t is 3 minus 2t. Okay, great. So what does this tell me? Now, we've talked a lot about this version, but let's talk a little bit more about this version. I could draw a little table for you, and then we could see the line being traced out in different ways. For example, at t equals 0, all of these would be 0. And the point that remains is 5, 1, 3. So that would be the x, y, z point on the line. I could also keep calculating here. How about t equals 1? Right? Then I would have 6 from here, I would have 5 from here, and I would have 1 from there. And we could keep going this way, and this is one way in which when a computer is asked to draw or sketch this line, this is what it will do. It will sample these parametric forms of the line and then plot all the resulting points. And you'll get some line in space. So let me show you what that line is through our CalcPlot 3D website that I like to use. So I've put in here, over here I've put the equation of the parametric forms of the lines that we got. How did I get this? I went to over here, select, and I put in space curve. We will again talk more specifically about space curves in a subsequent lesson. But that gives us this these boxes where I can put in the equations of the line. I didn't change anything here. The defaults are fine. I did go up here and change the domain for x, y, and z so that we can see the line. So I'm just going to pan around so you can, oops, what did I do? Oh, restrict view to 2D. I don't want to do that. Okay, I'm just going to pan around so you can see what this line looks like. So there it is. It is a line in space. And we can zoom out or in to see. Of course, the computer only graphs from -10 to 10 for t. So this is the extent of the line if you only go to -10, between -10 and 10 for t. Anyway, so there's the line. This doesn't look very much like what we had started with the different vectors for r changing as t changes. So to do that, so bear with me, I'm trying to get it, all right, that's good enough, to the standard view of x, y, z axis. To see how the vectors change, we can click on this trace button over here. And then you can see that as t increases, this is the direction of the line that we're going in. So that is an increase in t over here. So that's me moving that around. And then if I go backwards, if I decrease t, then I go this way. So here's another view on what's going on here. So that is exactly the picture that we were talking about. Each t value right here corresponds to a specific point that's being traced out over there at the endpoint of that blue arrow. So again, I encourage you to go ahead and play around with this, and you can plot all different sorts of equations for lines here, and you can zoom in, interact with them, visualize them. Great, so let me go back and talk about the last example. So in this example, we want to find the equation of the line that passes through 2 points in R3 and express your answer in both vector and parametric form. As in two-dimensional space, where 2 points determine a line, same thing in three-dimensional space, 2 points determine a line. So we do have enough information here, even though, as in the last example in the previous video, it seems like we have to do something different. So we have a point, so you can choose any one of these. We need our vector v to tell us the direction of the line. But that we can generate here by, if you imagine this is in 2D, and here's a point P, here's a point Q, and you want the line between them, you can just find the vector PQ, and that will give you the vector that points in the direction of that line. So that's what we're going to find here. So we're going to find the vector PQ. We'll do that by subtracting Q from P. So 3 minus 2, I'm doing here difference of x components. -1 minus 4, difference of y components. And then 1 minus -3, difference of z components. So I get 1, -5, and 4. I now have my v vector, And then I can go back over here, as I said. You can choose any one of these to be your P points. So I'll choose that one. And then write down my equation of the line. So this is a P plus multiples of V. So I have 2, 4, negative 3, plus multiples of 1, negative 5, and 4. And I asked for the parametric form also. So all we do to get that is combine the two vectors to then extract from that the x, y, and z equations. So I have 2 plus t, and then I have 4 minus 5t, and then I have negative 3 plus 4t. Great, so that's the parametric form of our line, and this is the vector form, or this one also. Oops, or this one also. Okay, so that's it. So this was intended to be a short video. We've done a lot of heavy lifting already in the first 2 videos. And as a quick recap, what did we learn in this video? Well, we learned that we can use some of the ideas that we had used to derive the equations of planes, specifically this picture, and help us derive the equation of a line in 2D or 3D space. Actually, this works in however many dimensions you want. We could write down the equation of a line in 37 dimensions. I mean, it's basically this. Each vector would have 37 components. So at this point, we got to a place where we understood this equation of the line as being very simply a generalization of y equals, this would be the mx plus b. So, you know, p is like almost, not quite, but p is like the point that you know is on the line. In 2D, we call it the y-intercept. You would start from there to graph the line in 2D. And then m is the slope. It kind of tells you the orientation, the direction of the line in 2D. That's like our v vector in 3D. And then x is just how far, you know, how long you want to go, how many times you want to trace that slope out in either direction. That's kind of like our t. And then we learned how to basically write this out in component form, and that got us to the parametric equations of the lines. And this tells us if we want to actually plot the line without using vectors, just as a set of points. This gives us a way to calculate what those points are on the line. And then we did a couple examples, and we also talked about skewness. So 3D lines, as a recap, can be parallel, they can intersect, and they can also be skewed, which means that, you know, they are on different planes, so almost 3D parallel, if you want to think of it that way. So that's it for this lesson, and I will see you in the next lesson 4.